Okay.
Yes, sir.
Okay. Yeah. So again, I think some of you signing a little bit late. Please come just before the class time. Okay. We will introduce a lot of informations, at the beginning of the class. Yeah, I leave sometimes for you to work on the project. Okay. And more will be here to help you answer your questions in the detail of the project. Okay. So now let me talk about this first project first. Okay. Let me share my screen. I have a project description posted on Moodle. Okay, let's look at this file first. Okay, so this is our project description. By the way, is everybody here? I have like more than 35 people here. We have more than that, right? We have students more than 40. So yeah, just tell your friend if they missed today's class, please watch the video and please come to the class. Okay, we have only maybe 6, 7 classes. Okay, don't miss any. Okay, so the first problem is a heat transfer problem. Okay, let me share the other screen. Hold on. Share my whiteboard. I need to write on it. Okay. So it's a conduction heat transfer. I assume everybody took heat transfer. Is that right? Or are you taking heat transfer?
I think a lot of us are taking it right now.
You're taking it by now. Okay. So, but I think this is okay. The first problem is a conduction heat transfer problem. I think so far it's almost at the end of the semester. Everybody should know the conduction, okay, extensively. Okay. So the first problem is a 2D conduction problem. Okay. So first of all, what do you mean by 2D? Okay. 2D actually means the third dimension is actually infinitely long. Okay, it's a third dimension. If you have a circle, then the third dimension is a long, it's a cylinder, it's infinitely long. Then every slice, every cross section, they are the same along the third dimension. Okay, so the temperature on every slice is the same. That's why we can assume it's a 2D situation. Okay, does that make sense, everybody? Okay, it's not like say the third dimension doesn't exist. Actually, it's opposite. The third dimension exists and it's infinitely long. Then every slice, every cross section is the same. Doesn't have any boundary effect on the third dimension. Okay, then we can assume it's a 2D problem. Okay, so let me draw some geometry here. Okay, so you have a material, solid material here. By the way, heat transfer is also, to me, it's part of the fluids, right? Heat is also like a flow. Okay, so conduction heat transfer, actually there's a heat flow too in the material. Okay, so imagine you have a material like this. It's an infinitely long bar, okay, along the, go out of the paper. The third dimension is, in and out of the paper. Okay, it's very, very long bar. Okay, this is just a cross section of that material. Okay, so when you heated the side, what happens? If you heat the sides, then the temperature will be transferred. The heat will be transferred into the material. Is that right? Everybody, that's the conduction heat transfer, right? So you have a thermal conductivity K, you can calculate the heat transfer rate, right? But it's a complicated problem. It's a 2D, right? It's not a 1D problem. So you have temperature. For example, you heat it. Let's say 500 degree K. Hold on. 500 degree K here. Okay, let's say 400 degree K here. So it's heated, right? It's more than room temperature. What is room temperature? Let's say about 300 degrees, right? Initially, okay, in the material, room temperature. Let's say one side is exposed to the convection, one side is insulated. That's the problem statement. So if you have heated surface, okay, so the temperature will increase inside of this material. Is that right? Okay. So, but what is the temperature distribution inside the material? First of all, if you do the experiment like this, you heat it, it won't reach to a steady solution immediately, right? It will take time, depending on the conductivity. It will take time to gradually, slowly reach to a steady condition inside the material. Is that right? Okay, but it's not a uniform temperature inside the material. Do you agree? Some place is hotter than the other places. Everybody follow me? Okay, for example, the point near the 400 degree here would be cooler than the point location near the 500 degree here. Okay, so one of the topic in heat transfer, conduction heat transfer, is to calculate the temperature inside this material. It's not the one temperature, it's like a temperature distribution. Everywhere is different. Okay, so in 315, do you know how to calculate the temperature inside this material?
I remember we used matrices to do it.
That's actually the CFD. Okay, they use the numerical method. There's a one chapter in heat transfer book talk about using the write down the breakdown into the matrices, right? So it's a numerical method. Basically, it's approximation, basically, right? So that's exactly what the computer actually do for you right now. Okay, Fluent will calculate that for you, but analytically, it's really difficult. You know, there's no analytical solution for this. Okay, there's a 2D differential equation, right? It's really difficult to calculate. It's difficult to solve depending on the boundary conditions. It's a second order. It's two-dimensional. You have a partial t squared, partial x squared plus partial t squared, partial y squared, right? That's not easy to calculate, to solve analytically. Okay. So here, what we want to calculate, the goal is to calculate the temperature distribution inside this material. So let's say this side is exposed to convection. You have a convection going out this side. This one is convection. You have a convection heat transfer coefficient, okay? You have an ambient temperature here. And then this side, let's say, is insulated. I'm pretty sure with this type of boundary condition, there's no way analytically you can solve that differential equation for heat transfer. Okay, so then let's find out the temperature distribution inside. So how do we find out temperature distribution? We need to have the grade, right? Remember we talked about this grade in my introduction. I draw very coarse grade. In the reality, it's much finer than this. Let's say if you have a grade like this placed on this material, okay, the Fluent, the software will calculate the temperature on those dots and marked it with field color on those dots. That's how many dots here? Depend on how many grades you put, right? For this grade, you have 1, 2, 3, 4, 12 unknown points. Okay, this is just the chapter, one of the chapter in the heat transfer book, right? So we make it hands-on, let you actually run it using the computer. Okay, by solving the differential equation, whatever, discretize the equation, then they can calculate temperature value on these grid points. Okay, eventually Fluent can calculate for you, and you can output it to using contour, temperature contours. You use color to see the temperature distributions. I have a tutorial posted. Follow that today. You will see what kind of a result you expect to see. Okay, so this is the base case we want to simulate. Okay, but physically, let's talk about the physics. This is a transient. It is a transient phenomenon, right? It's unsteady. Initially 300 degree. But at the end, you know, it will reach to a steady state. solution. Do you agree? There's no way you get temperature like 1000 degrees somewhere. It will always bounded based on the boundary condition you put it in there, right? In other words, if you let the experiment run long enough, you can do actual experiment like this. Okay, you choose a material, a rectangle like this. You heat it to the surface with temperature. One side exposed to air, one side insulated. This is actually an experiment. It takes time. You're gonna wait an hour, maybe 20 minutes for the temperature gradually developed inside this material, right? So it is a transient process. Okay, it's a transient process. Fluent can do two things. It can give you a steady state simulation, steady state solution. It also can do unsteady simulation. Let me talk about one by one. Simulation, steady state simulation. Okay, what steady state means is eventually this situation will reach to a steady solution. So directly, okay.
In an elevator. I fucked her in until she couldn't walk. Then she choked on this massive cough.
Who's talking? Could you
I then
mute
fucked
yourself?
her in the butt.
Hey, bro, mute your mic.
This is the governing equation, which I'm talking about, the general equation conduction. I get rid of the convection terms, so it becomes simpler, but it's really not simple. You can solve it. Basically, I don't think with the T there, you cannot solve, okay? So what steady state means is, hey, let's assume eventually it reaches to steady state. It doesn't, temperature doesn't change with time anymore for every point here. Okay, so it becomes 0 for the right hand, left hand side. So that's the equation Fluent solve if you click the button steady state. Okay.
Is that partial derivative of temperature over time equal to, or is that plus or minus?
Equals. Let's see the equation, right? You have to have an equal sign. Okay. So the governing equation for the conduction is actually generally is that you should have the partial T, partial time terms. Yeah, it's an unsteady process. Okay. But if you only care about the final solution, okay, I don't care about the process, how long it takes, how it gradually change the temperature. If you don't care about those, if you only care about the ending state, okay, you can select the steady state simulation. Okay, then let's say partial T equal to 0. You have to make that assumption. Okay, but remember, be careful. In a lot of cases, the partial temperature, partial T is not 0. No way it will be 0. So if you force that assumption, sure, Fluent still will give you some result. You can force the assumption. Let's say, let's do the steady state simulation for that case, for that problem. But if there's no steady state solution, if the thing is always changing, like a lot of cases I show you in my introduction, the airplane, you know, those vortices, it's changing all the time. There's no steady state solution. Okay, so then it's wrong. You force it. If you click the button, say steady state, then the Fluent will get rid of that term, partial T. It will calculate something for you. It gives you color picture, give you great result, but they are totally wrong. It's garbage in, garbage out. That's what I always say. So the assumption you made here has to be valid. Okay, do you see my point? It's very dangerous for the software such as Fluent. Okay, Everybody, somebody that don't know much about fluid mechanics, don't know much on heat transfer, they can still get a result from the software, but that it's garbage. Okay, be careful. That's the thing I want to convey here.
Dr.
Okay.
Zach,
Yes.
when would it be necessary to use a steady state?
If you know the situation, the physics of that problem, if you know there will be a steady state solution. Just like this problem, I'm pretty sure there's a steady state solution for the conduction. Okay, then you can use that to help you get the steady state solution. See, you're running Fluent, you need to know some fluid mechanics. You need to know some heat transfer. You need to have the physics background. Okay, otherwise you making wrong choice, then it always give you solution. Okay, that's bad. Okay, that makes sense? By the way, do you agree this situation will have a steady state solution at the end? I want everybody to agree with that. Is that right?
This is on just a plane.
This is a
thickness.
cross section. It's a cross section of an infinitely long material bar. It's the third dimension is going in and out the paper, vertical to the screen.
But it's
Okay,
not
so-
accounted for under the situation that we'd be running for this simulation. This would just be on the plane.
Yeah, you're just on the plane because I said it's infinitely long on the third dimension. Then on every cross section, their temperature is the same. There's no change along the third dimension. That's why we can simply say it's two-dimensional. The other dimension is infinitely long. Does that make
So-
sense?
Yes, sir. Would it be unsteady state then for any other with the third dimension involved or no? Or would it still be?
You answer me. See, that's now it's a challenge for you, for your knowledge of heat transfer or fluid mechanics. Okay, you see, you have an infinite long bar like this. You infinite, each side is, you keep 400 degree, keep 500 degree, keep insulation. Okay, the other side keep exposed to air. Okay, do you think there's a steady state condition at the end if you do experiment like that? If you leave it like that for 2 hours,
Yes, sir.
and then you leave it there for 3 hours. After 2 hours, you check the temperature. After 3 hours, you check the temperature. Will they be different? That's the definition for steady state or unsteady. If it doesn't change with time, of course, there's still changing on the space, you know, spatially, it's the temperature all different on all those 12 points. But I'm talking about for each point when you compare at a different time. Okay, it should reach to a steady state. It won't, if you run long enough, eventually it won't change anymore. Does that make sense, everybody? Did I answer your question, Chris?
Yes, sir. Thank you.
Yeah, if it's infinite long as each side you keep the same temperature, you know, it shouldn't change after a while. So for this case, you know there's a steady state solution at the end. Okay, so you should be able to click a button, say, hey, steady state. So Fluent will get rid of the partial t term, will be 0. So it will calculate the simplified equation for you. So it will tell you all the temperature in terms of x and y. Okay, so that's a steady state. So it's okay to do steady state for this problem, as long as you don't care about how long it will take for the temperature to reach to that steady state. Okay, as long as you don't care about that. If you only want the final solution, go ahead, do steady state. But as a full engineer, another criteria, another thing we want to know is, hey, doing this, if you want to heat this material, how long do I need to heat and it will reach to a stable solution? That's something actually we want to know. Okay, if this material is gold or this material is wood, but educated guess, do you know which one take longer? to reach to a steady solution? Which one is more conductive?
Gold.
The gold, right? Then it matters. Look at the equation here. Actually, this is the general equation, right? K over rho Cp, right? Partial T squared, partial X squared plus. This is a differential form of the energy conservation law, right? So that matters. So this thing, if it's there, unsteady, okay, it is an unsteady problem. It will be good to keep it there. Eventually, it will reach to a steady state solution, but it takes time. You know, you will know how temperature change in terms of time if you solve this complete equation. Okay, that matters. You see, the K matters here. K is there. If you look at the steady state equation, if the left-hand side is 0, the K doesn't matter actually. It's a constant. You can cancel. Left-hand side is equal to 0. Okay, doesn't matter different materials. Eventually, you're gonna get the same solution. Wood and the gold, eventually the temperature distribution inside the material, it will be the same. As long as your boundary conditions are the same, okay? It will be the same. But the difference is it takes longer for wood to reach to that steady state solution than the gold. Okay, that's the difference. So it will tell you how long it will take, okay? What is the transient? What is the temperature at in different instance? For example, you start the simulation 8 o'clock. What temperature will be at 8:05 for gold and for wood? There will be different. If the gold need 5 minutes to reach to steady solution, it already steady temperatures. But wood probably need 5 hours to reach to the steady solution. So at the 5 minutes time, it's totally not the same as the gold. Although at the 5 hours later, you will get the same temperature distribution for the wood comparing to the gold. But at the 5 minutes time, it's totally different. Okay. If you do an unsteady simulation, it will tell you at any time instance what the temperature will be inside this material. Okay. Does that make sense to everybody here? This is just like you do experiment. I mentioned it during my introduction. Doing CFD is just like you do experiment. Exactly do experiment in computer. You tell what Fluent do for the experiment. Okay, they select the material. Okay, I place the temperature 500 degrees on top. Place the temperature 400 degrees on the left. Okay, exposed to the air in the right. Just tell Fluent what are the conditions. Then Fluent do an experiment. Okay, so in the experiment, just like, hey, you do experiment, you put sensors in there, temperature sensor. I put 12 different temperature thermometers inside the material to measure the temperature. Okay, so at 1 minute, let's see what the temperature is. Oh, I give you temperature values at 1 minute. At 2 minutes, what temperature is. 3 minutes, what temperature is. Okay, the experiment is temperature change with time, right? So it would tell you, just like Fluent can, just like doing experiment. Okay, Fluent, you can put the sensors on the grid points, okay, inside the software, and you can record the data. Okay, you run for an hour, for example. You specify Fluent, let's run it for an hour. Okay, then let's put a time step, 1 second for the time step. So you will run 3,600 time intervals. Okay, these are the things you need to specify for unsteady simulation. How long you want the experiment to run? What is the time interval? Okay, so every second you can output some result to see what the temperature inside. Okay, so it will show you the changing temperature distribution of the material. Okay, that's eventually what we want to see. And this type of experiment, CFD, is extremely accurate. Actually, it's very accurate. Okay, so it basically can just tell you within 1% errors comparing to the real experiment. Experiment may have more errors comparing to the reality. Okay, than the CFD in here in this kind of application. Okay. Okay, so that's the background of this project 1. Okay, Now, any questions so far? It's really important for everybody to fully understand this the physics of this project before you actually start. Any questions? Is that good? Okay. Now let's look at the project descriptions. There are some tasks I want you to do. Okay, here we go. Okay, so at the beginning, I'm talking about the configuration of the geometry. It's 1 meter by 0.6 meter rectangle material, just like I draw on my whiteboard, right? 1 meter is width, 0.6 meter is the height, okay? So top and the right, oh, okay, on my drawing, I put the left side temperature. Actually, in the project description, it said top and the right side of the boundary, you need to specify two different temperatures. It's up to you. I don't, I want everybody use different temperatures, okay? So specify some temperature at your choice. You can even specify cooler temperature, it doesn't matter. Cooler or heater or hotter, it's okay. Or maybe one side is hotter, one side is cooler. It's really up to you, any values, okay? Bottom boundary will be insulated. Okay, there is a condition called insulated condition, which means the heat flux equals 0. Partial T, partial Y equals 0. That's the insulated condition. I don't know if you fully understand this in heat transfer class. Okay, I hope you pass the heat transfer class, first of all. Okay, so insulated means no heat flux going into the boundary. Okay, so heat flux equals 0. The left boundary will be exposed to air. Okay, Fluent is also able to simulate a condition, convection condition. Okay, so you need to input the convection heat transfer coefficient of air. I need you to do some research. What is the convection heat transfer coefficient of air? The H changes with temperature as well as change with the flow speed. Okay, pick a value. You have to justify the value you pick. You say, hey, because the temperature I put it down there is near 300 degrees. So that's why I pick the H based on that temperature. And also I assume there's a speed, wind speed of 1 meter per second. Okay, that's why I find that the heat transfer coefficient of air is this value. Is for satisfy the 300-degree temperature and the 1 meter per second speed. Okay, I want you to do some research on heat transfer, convection heat transfer coefficient of the air. You need to input that value into Fluent. Okay, again, I want everybody has their own choice. Okay, so eventually you will have different results. Okay, nobody will copy each other, right? Okay, so, and initially the temperature of the material will be the room temperature. Room temperature will be 300 degree K. So is that 300 degree K? 273 is freezing point, right? So 27 degrees Celsius, yeah, that's about right. Okay, it's about 75 degrees Fahrenheit. So 300 degree K is perfect for the room temperature. Okay, so these are the conditions I want you to specify. Now let's talk about the grade. Okay, 1 meter by 0.6 meter, you can divide it into, you know, if you put the grid size, the size of each grid cell 1 meter, I'm sorry, 0.1 meter, then it will be 10 by 6, right? 10 by 6. So that's the median grade. So it's 0 meter. So you divide each dimension into 10 grid cells. Okay, so 0.6 divided by 10, there will be, I'm sorry, 1 meter divided by 10 grid is 10, right? 0.6 divided by 6 grid, so it's 0.1 meter, the grid size. So your grade will be square grade. Okay. Let me share my screen again. Okay, so your base case median size will be 2, 3, 4, 5, 6. 6 grade vertically, 10 grade, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh yeah, it's already 10, right? Did I count it wrong? Okay, 10 by 6 grid. Okay, notice you have a 10 grid spacings, 10 grid cells along the X dimension. Let's say X and Y. So the spacing is 0.1 meter. Okay, so it's a square grid. Okay, easiest to make. Okay, notice the nodal point is 11. See, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, be careful. The spacing is 10. The cell number is 10, but the nodal number is 11. Okay, it matters when you do outputs. Okay, and also 1, 2, 3, 4, 5, 6, 7. Okay, so you have a center point, right? Center point will be 6 and 4. Okay, if you use index. Okay, does that make sense? Any questions?
Why there's no 0 point like the origin?
Doesn't matter. This is the index. You put it in there. I don't care. You start from 0. It's okay. From 0 to 10. Okay. I like to start from 1. You know, number 1 grade. It's clear to me. Okay. So Fluent will if you look at the tutorial, it will help you. It will generate the grade for you if you just enter the grade spacing. Okay. So that should be okay. Let me see. There's some people joining. Okay. Good. Okay. So that's the layout. I'll share my screen again. So I want you to run 3 different grade levels, 5 by 3, 10 by 6, and 20 by 12. The reason I want you to run the 3 cases for you to compare. Okay, as we mentioned the last times, how do you know what grade resolution is appropriate? Because we mentioned last time, if it's too coarse, it's not good, right? We just approximate the equation, nonlinear equation into linear equation between 2 grid cells. Basically, it's a straight line between the relation, like straight line between 2 adjacent grid cells. So if it's too coarse, it's not good because you have a curve in between, right? So, you know, obviously too coarse is not accurate. But what about I have to put 2 million by 2 million grid there? It will run them like a days for you on your computer. Okay, it's too expensive in terms of the computational cost. So there will be a optimal number of grade resolution for each individual case. Okay, and I don't know what is optimal resolution, and you don't know when you do a real project. You really don't know what should be the mesh size resolution. Okay, so one way to test is you test different grid levels. For example, you test the 5 by 3 first. That's 0.2 meter, the grid size. Then I divide it into half, 0.1 meter in the size. Let's compare the result. If the result is the same, that means my 5 by 3 is fine enough. You know, you don't need to refine it anymore, resolution. I get the same result. Why bother? Right? I save my computation time by using a coarser mesh. Okay, so I'm pretty sure if 5 by 3 is the same as 10 by 6, 10 by 6 will be the same result as 20 by 12. Okay, do you see my point? You're doing the experiment for a same size. The only difference is you place more grade or place less grade on it. Okay, the same condition, same simulation. So it turned out to be, for example, you can check the center point temperature. Oh, okay, it compare exactly the same between 10 by 6 and the 20 by 12. Okay, that's good. I stop here. 10 by 6 is good enough. If I refine it, the result will be the same. Then if I refine it again, like 40 by 24, it will be the same. Okay, then I stop. That's the way we decide the grid size. You need to run different resolutions to compare. Okay. Does that make sense to everybody? Okay. Okay, so before I talk about the requirement down there, 1, 2, 6. So today, by end of today's class, I want you to make your decision on material. Okay, you need to turn on the Fluent to see what's the material available in Fluent database. Okay, or maybe some of you may not be able to finish running the geometry and mesh. Maybe by end of the next class, Wednesday's class, you need to tell me, okay, submit the material and the temperature values, okay, boundary conditions into the comment area of the summation site. The summation site is already open, the project summation, okay, but you can type in the comment what material you're going to use and what temperature values you're going to use. And also what heat transfer coefficient. Maybe I didn't write the heat transfer coefficient. Maybe you can find out and write down the heat transfer coefficient too. So I just want to see everybody to have different values. Okay. Okay, so let's look at the requirement on the report. Okay, 6 items I want to see on your report. Okay, so I like you to run the steady state simulation first. Okay, because this problem has steady state solution. Okay, as we talked about earlier. So if you click the buttons, try to use a steady state, it will simulate a steady state solution for you. There's no history, okay? Nothing in between. It just gives you the ending data. It still takes some iterations, but that's nothing to do with time. It's just taking iterations to eventually reach to a converged solution, okay? So that's how it runs. So it will run iterations. So the first try, it won't get you final solutions. Okay, it will keep iterating depending on how difficult the problem, complicated the problem is. Sometimes 6 or 7 iterations enough. Sometimes it need to take hundreds of iterations for Fluent to reach steady state solution. I remember some of you take my Fluent class. We have the iteration project, right? Use Excel to do some piping calculation iteratively. Similar idea. Fluent will do iterations, okay, to reach to a converged solution. Okay, the converged solution is the useful solution at the end. Okay, before you reach to the convergence, the solution is garbage. Okay, don't even need to look at it. You need to only look at the solution after convergence is reached. Okay, so when you run, it will show the convergence history, the relative errors between this run and this iteration and the last iteration. It will plot the relative error versus the iteration on the screen. Eventually, the relative error will become less than 10 to -4. Then Fluent will stop the iteration. That means the solution is converged. Okay, so when you run it, it will show on the screen. Okay, I want you to screenshot it and copy and paste the screenshot of the convergence history onto your report. You have 3 cases to run here: 5 by 3, 10 by 6, and 20 by 12. So you will have 3 convergence history plots. Okay, just the evidence showing that your solution is converged. Okay, I assume you know how to do screenshot. If you don't know, find out. Okay, screenshot and copy and paste the plot. Okay, then this is the first item, right? I want to make sure you reach the convergent solution, converge the solution. The second item, plot the contour of the converged temperature field. So at the end, after you converge, the fluent will stop running. Okay, then you can, there's the function called contours. You can display the contours. Okay, you choose the contour, choose the temperature value. It will plot the temperature, color temperature contours inside your domain to show the temperature distribution. Okay, I'll leave it later. You will see it on the tutorial how to do that. Okay, but that's what I want to see. For all three cases you run, I want 3 contours. Okay, so you can also screenshot it and copy and paste on your report. So this is the easy requirement for the steady state simulation. Okay, 2 items you needed. Okay, for all the 3 cases you run. Okay, for the steady state. Okay, now then it's the transient. So this is a trend depend on the material. It could take longer or shorter to reach to a final state. Okay, so the third item is plot and compare the history. So I want you to decide now. You haven't decided the mesh, which grid size you want to use. Now you have 3 choices: 5x3, 10x6, and the 20x12. Okay, I want you to compare the center temperature history. Okay, the history from the beginning for the transient simulation. So from the first second, third second, 100 second, 200 second, 500. So you have a plot temperature versus time for the center temperature of the domain. Okay, so put the 3 plot, use Excel. Fluent can allow you to write out the temperature history to a text file. So you can have a text file for temperature history for the center point. So use Excel to put the 3 curves together into one plot. Then you can compare. 2 of them will be close to each other than the other one. Okay, so then I think probably the median size is good enough. Okay, it will be close, very close to the finer grade. And the coarser one may be slightly different comparing to the other 2. So by looking at this result, then you can decide which grade you want to use. Okay, that makes sense? That's the standard process to determine the grade, appropriate grade resolution. Okay, this is number 3. So show the evidence, show the plot with 3 curves in there, and make a decision which grade you are going to use, which grade is appropriate for this project. Okay. And from the center temperature history, center temperature will be a gradual change. Eventually, it will converge, reach to a flat line. If you look at the temperature history, center temperature history. The reason I want to choose the center, because center is the furthest point to the boundary. It takes the longest time to reach to a stable solution. Does that make sense? If the center point is reached to a steady solution, rest of the domain all reach the steady solution. You can assume that. That's why we want to check the point that take longest to reach stable solution. If that point satisfies, everything else satisfies. Okay, so if you look at the center temperature history, it's a gradually increase, then or gradually decrease, but eventually it will reach to a flat line. Okay, because the temperature doesn't change anymore if you run the experiment long enough. Okay, so I want you to determine how long it takes for this center point to reach to that steady state condition. Okay, because this is the history plot, it's the temperature versus time. So in the x-axis indicates the time and become flat, the curve become flat. Okay, so that's how you determine for your material how long it takes to reach to steady state. Is the logic sound? I'm checking the center point. Is that enough? Do I need to check other points? I don't need to, because this is the furthest point to the boundary. It takes longest to reach to steady state. If this point reach steady state, everywhere else reach the steady state, okay? Number 5, plot the temperature contours. So now I want you to, now you run transient simulation. So you know the history, how the temperature changes. So I want you to output at different instance, the temperature contours, the temperature distribution. For example, it take you 2 hours to reach the steady solution. So let's say, hey, at the 5 minutes, what the temperature looks like, the field, right? The temperature distribution. It's a 10 second. What does it look like? 20 minutes. What does it look like? So choose 4 different times. I didn't say how many, but 4 should be enough. Okay, to plot the temperature contour to show the temperature, the evolution of the temperature distribution inside the material. How does it change? Okay, great. It's a gradual change. You know it's a gradual change, but how? We want to see what the temperature at a different moment, different time. Okay, so this is number 5, and number 6 is, these are all the results from 1 to 5. Okay, number 6 is a discussion. Again, all my report, when I need you to discuss your result, okay, to talk about the physics, talk about what's the result tell you, okay, this kind of things. Okay, so this is a complete report. And for outcome 4 to 6, notice number 3 items is to determine the grid size. So after you did the number 3, you decide what is the appropriate grid size. Okay, so item 4 and 5, just use the grid size that you determined, the result from that grid size. Okay, to show 4 and 5 items. Does that make sense? Okay, so 4 and 5 basically, and including 6 discussion. You only need to discuss things about using the grid size, you know, you determined. Okay. I guess that's it. That's all I want to talk about for this project. Okay. Any questions so far? I guess you will have probably more questions when you actually doing it. Okay, we have about 25 minutes here. Let's start working on it. There's a tutorial. There's another file I posted in Moodle. It's called tutorial, project 1 tutorial. It shows you step by step from the beginning, starting from turning on the software, okay? And what's the step you need to take to reach to the solution, okay? So practice with the tutorial. It's not the same case as this project, but it's similar case, okay? Go through it from the beginning to the end without the errors. The end, it's good for you. You kind of know how to do, okay? So that's the practice. So we don't have much time, 25 minutes here. You can start with it to know how to turn on the Fluent, know how to turn on the workbench, okay? You need to practice it at home, okay? By the beginning of Wednesday's class, I assume everybody went through the entire tutorial, okay, successfully, okay? So you can start now. And I think there's 2 processes here. First is to generate the geometry and the mesh that use on the, first you turn on the ANSYS workbench, okay? Pick the geometry module to draw the geometry. Then start the mesh module to place the grade, okay? Then you import that, the file, you generate a mesh file after that. Then import that file into Fluent. Fluent is the simulation package. Okay, then you run it and produce results. Okay, that's the process. Go ahead, start working on it. Okay, any question? Mo is here and me and I'm here. Yeah, any question? We're more than happy to answer. Okay, let me stop the recording here. I don't think there's anything else we need to record.